was never said or heard. Happy ever after? I don't think so. I'm in love with someone who doesn't know I exist. I stare from afar in my hand, broken heart while I play pretend. I'm in love with someone who doesn't know I exist. And it's you, yes, it's true.
Hello, we are so glad to see you on campus. There are a few things that we need to let you know before we start the lecture. First, please make sure that you have your mask on all the time when you are in the classroom. Also, please make sure that when you are having a seat, try to keep a social distance with others if possible. If you feel sick, no matter it's physically or mentally, please stay at home. We do provide various online resources to keep you learning. Now, please sit back, relax, and enjoy the lecture. Well, I hope you guys appreciate the amount of effort we put before each lecture, given that, you know, the TA and I record such a cute video, and I'm so sad that why there's always echoes like this. This time I do, oh, come on. Is there any audio expert can help me figure out how to get rid of this echo? This time I do use, let me see, select.
Can you guys hear me? I believe yes. Yeah, but now the issue is that we have an echo here. It's like a loop. How to deal with this? Mute your computer. Yes, you guys said everything. I did. I mute my computer, man. Don't ask me to do that. Yeah.
I think both of them have both microphones open.
No.
No.
Yeah, only one of them open.
Can we ask for ID?
They are not come right now, and I don't want to wait because we are pretty tight on schedule. You know, what can I do? This is probably what I would do. Hello, can you guys hear me now? Okay, awesome. I will just use my voice. I'm loud enough. Okay, so we are partition pages into fixed size chunks. And whenever I want a page which is not found in the system, it will trigger an exception called page fault. And the operating system will handle this page fault, try to figure out where should I put this page in the physical location, and then perform operations working together with the hardware to put stuff in the physical location and change the mapping to that the virtual memory subsystem know where the page is physically is. And whenever there's a page fault, we do all the same. And this is how we get stuff into the memory gradually when you are running this program. And the idea of partition your memory spaces into fixed size chunks is called paging. And loading each page on demand is called demand paging. And whenever you have a page that is not found, that is called page fault. These are three different terms that I don't add them all together. So we said that the most frequently used mechanism is called demand paging. However, in the past we use segmentation, which is instead of partition your memory space into fixed size chunks, we allow variable size chunks, and this is called segmentation. And as you know, with segmentation, we are running into the trouble of having the external fragment and internal fragment, right? And especially the external fragment was a really big issue for us. That's why we are now in favoring the demand paging. So, but one of the overhead that you identify in the last lecture is that if we want to do demand paging, then the page table is an overhead in terms of the space required for storing the translation table, because instead of just a few segments that you need to record the starting address, now you have to record the starting address for every page, which is really small compared against the whole virtual memory address space. And so as you practiced before, right? If we are now in a 64-bit address space, it turns out that it's an enormously large size that cannot even fit into any of the system right now. So this idea is not going to work. So we gradually try to fix that. So first of all, if we want to get rid of the problem that your page table is occupying a contiguous space, then you have to make them page. So in each of the page, as you know, it's 4 kilobytes in modern systems. And if you have a 64-bit address space, meaning that each of the memory address is 8 bytes. So that's why each page table entry is about 8 bytes. And if you have a page with 4K, and if you have 8 bytes for each entry, that's why we got 512 at the end of each page table node. However, there are more things you can do with this. So for example, most of the time when we are running our program, except for the code section, which stores your instructions that needs for the running the program, which is pretty dense in the very beginning of the area, and a pre-compiled section called static data section, initialize all the global variables, which is also dense. Then the heap area starting right at the end of the data section, and the stack area coming from the back of the virtual memory address space of the user space. It's pretty sparse in the middle for the virtual address space. So to shrink the size of a page table, an idea is that, well, we can also create a page table nodes on demand in a way that only when those addresses are used, we allocate a page table node. However, now the next problem is that, okay, you have a lot of page table nodes, they are not contiguous, so you still need a structure to locate them. That's why we create B trees for us to easily index this page table nodes. So that's where we are from. But if you review what we have taught so far, simply paging or segmentation help us to address the issue to share a single pieces of physical memory to multiple applications. However, it doesn't address the issue that, well, if my program is larger, or if the total amount of memory I need is larger, or if I have a program that was previously returned in a system with larger memory, and I want to fit it into a smaller memory. So how do we get this working? The mechanism is actually swapping. So today we are going to start with swapping, and then we are going to see two classical memory system design from two operating systems. One is from the VAX, and the other is from the Mach operating system. So we talk about demand paging and the mechanism behind demand paging to support the fact that we don't have sufficient amount of physical memory when we are doing the demand page, when we are running the demand paging in the front end, that is called swapping. So the basic idea of this is that, well, first, if I have an instruction to access a virtual memory address, and how do I know if the page, where is the page? Now you know, you have to look up the page table. However, if I don't find a mapping between physical location and the virtual address, you know, this now we have an issue called page fault. So whenever we deal with the page fault, we have to figure out where to put a page that you are going to loading in to, right? So then you have a page replacement policy. And however, most of the time, you run this issue because you are running out of space in the real DRAM. So you have to figure out, well, which page to kick out. So to provide a place to store those pages being kicked out, that's called a swapping space on the hard disk drive or the secondary storage. Then you have to kick some page out using a page replacement policy, temporarily store it in a secondary storage. And finally, once you have that done, you can put the desired page into the free up space. So that's the whole picture of demand paging plus swapping. Again, demand paging will trigger page fault, and page fault would require the page replacement policy to handle where am I going to put the demanding page and figure out where is the location that I should put the page, and if there is someone there, I have to kick it out. So the process of kick the page out is called swap out. And when you are doing demand paging, if you are loading a page from a swap space, it's called swapping. So that's the whole the high level idea. So the big picture here is that, well, demand paging plus swapping is that, first of all, you partition your memory address spaces into fixed size unit code pages, and allocate a physical memory page whenever the virtual memory page containing your data set is absent. And in case you are running out of physical memory, reserve space on this. as the swapping state. And but again, right? Remember that your secondary storage is really, really slow. So for example, the access time of your hard disk drive is around 10 milliseconds. And how fast is your processor? Do you remember? Yeah, how fast is your processor? Let's try this. Microphone there. Okay, so how fast is your processor? Do you guys remember? Yeah, for 40 hours processor, how fast is it? Like, what's the latency? What's the raw scale? So we said the hard disk drive is around 10 milliseconds, right? So if you have a 4 gigahertz processor, right, it's divided by 4 times 10 to the 9, right? So it will be around 0.25 nanoseconds, right? So it was less than 1 nanosecond. So it's orders of magnitude faster than your hard disk drive, right? That's the processing speed that we are with. So you know how slow the hard disk drive is, right? So remember this thing, right? This 2 gigahertz processor, 0.5, right? And with your hard disk drive is really, really slow. So now a question that I'm going to ask you is that now you know that hard disk is really slow. And page fault, let's assume it's not page fault swapping is not frequently happen. Let's say just 0.1%, right? It's a lot lower than the rate that you will get COVID. So with this low rate, how much slower comparing with the case where there's no page fault, there's no swapping? Hello? Are we getting better? No. Gave up. Hello? 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 You guys hear? Is it better? Okay. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see what you guys think. Done. Okay, definitely we need some discussion. So go ahead, discuss with your friend for another minute or two. All right, try to wrap up. Well, we guys still have a minute. No worry. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see. After discussion. Oh, all right, so definitely we need some work, right? So can I have some of you sharing your thoughts with us? Hello, someone here? Okay, you want to? Okay, so what do you think?
So the base is memory reference is about 100 nanoseconds.
Okay, so the baseline is 100 nanoseconds, right?
So for hot disk, so we have 0.99%.
So 0.99. So 0.99 times 100.
And the 0.001 times the speed of hard disk. So I take the 1 megabyte sequence from this. So there's 2 times 10 to the 7.
Okay. So if you take this one, that will be 2.5. Oh, you know what? What's missing here? You also have to include this one. Right, because you have, okay. Okay, so this is interesting, right? So you were saying, well, you were saying about this, or you say this?
No, it's about the what?
Okay, 20 milliseconds, right?
Yeah.
Okay, so then this is what you get, right? So this is what we get.
Yeah, so it's about
99.9 plus, wow, this is a lot, right? 1.10 to the minus 3 times, if we scale everything to nanoseconds, this thing will be 20 times 10 to the 6, right? So then this one cancel out, this will be 3, 99.9 plus 2. Wow, that's a lot, right? So
even if I add this thing, I think it's relevant.
yeah, it's about this, right? And if you don't have that, right, it's just 100, right? See that? Even though we have just 1%, right? So see that? So it's about 200 times slower, right? So I would say like B is probably the closest estimation, right? So here's the thing, 0.1% sounds really small, right? Like right now, if you go to Costco, you probably would get higher chances of meeting someone who were previously having COVID or something, right? But so this is a really low chance. I hope our COVID infection rate is like this, right? With this low rate, you still get 100 times slowed down, right? So one thing that we know of is that, the page replacement policy, if you want to use swap is a scheme that enable us to share the limited physical memory space freely. However, it's never for the purpose of efficiency. In fact, you should avoid swapping page in and out if possible. Right? Once you swap frequently, your system is going to be really slow. So that's why when you design an efficient application, the usage of memory is really an issue, because if you use memory intensively, you will have a lot of issues of swapping in and out. Right. So that's why that's really a big issue. And when you are talking about page replacement policy, our goal is that we want to avoid future page faults. Right. So and the reason is because swapping in and out is really a big overhead. Okay, so before we're talking into the design of modern operating systems and their virtual memory system implementation, let me put you guys in the big picture that connects everything from 203 to 202 together. So in 203, this is what you know, right? You have a processor has many cores, and each of the core has its own register, its own cache, and TLB. And the TLB stands for translation look-aside side buffer, is a page that pages the page table entries. So it contains the translation of your virtual to physical address map. There is last level cache, typically shared among multiple cores, and DRAM, where your default system name memory, and storage. Now you know serve as the swapping space. So say that I have a program, I try to access a memory page in a virtual memory address space. Right, this is virtual. So now I need a translation to know where it is. When you need a translation, you potentially need a page table. However, the page table resides in that memory or disk, which is really slow. So that's why we have the TLB. So for this case, right, if I'm referencing this page, and if the page has a translation entry resides in the TLB, I don't have to go to the page table. Instead, I will always consult the TLB first to see if, hey, did you see the page that I'm looking for? And if the TLB says yes, this is the TLB page, then everything else is potentially can be satisfied by the data cache, last level cache, or your DRAM without visiting the real page table. However, if I am referencing another page, for example, this one, and the page table entry is not existing in the TLB, then I ask the TLB, it's called the TLB next. Then you really have to traverse the page table. So when you want to traverse the page table, first of all, in the last lecture you learned, one of the registers in SADC processor called CR2 register records the physical location of the root node of your page table. So with that register pointing to the location of the root node of the page table, which you know is also something resides in the DRAM right now. You will have a DRAM reference, and then you will have to gradually traverse the whole tree, which potentially incurs more DRAM references or even storage references until you find the last level page table entry like this one. And this entry will contain the translation you want, and in the meantime, you push these entries to TLB and load the page from the storage all the way, push it to the processor for your continuous application. So this is the big picture. Hopefully that will give you some idea how the hardware and software work together when we are running your application. As you can see, right? If you look at this whole flow, TOBness is a really expensive process. And if the TOBness is also a page fault, that would be even more and more expensive. So these things are the things that we definitely want to avoid in real practice. And now let's see how operating systems try to optimize for this. So the first paper that we are going to study is virtual memory management in the VAX EMS operating system. Again, you read a paper, and we know it's important to figure out the why of each paper. So why don't you go through this question? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let's see what you guys think. Okay, we got unanimously agree on, well, mostly C. So can I have some of you telling me why do you guys think C is the right answer? What are the evidence that will convince you about C, the answer of C? Why do you guys think C is the most relevant one? Any thoughts? The second and the second. The first and the second are correct. You write that in the paper. How about the third and fourth? What do you guys think? Did the paper say anything about that? The fourth one is correct. Where did you find that?
The first point is major concern.
Major concern, okay.
Effect of one or more heavily.
Okay, right? So here's the thing, right? If you read the paper carefully, everything is here, right? The system needs to execute various types of application efficiently, among different types of hardware. As a result, the memory management system must be able to do blah, 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 right? So it turns out that we need to, the first one kind of like implies that, right? You need to reduce the inference from heavily paging processes. The second one tells you that you need to reduce the overhead of page tables, right? And then reducing the startup cost of the program, reduce the disk load per page, right? So it's implied, it's not directly mentioned in the paper, but it's implied by this paper. So now, knowing that the goal, these are the four goals of the paper. And then, well, these are the why, right? And when you design a system, you always start with the why, the big problem, the big picture. Then you design mechanisms proposing those whats to address those whats. So this paper has quite a few optimizations. Can you tell me which of the following combination between the optimization and the goal is incorrect? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's see what you guys think. There's no option. No, here we go, right? So looks like we definitely need some kind of discussion. So why don't you go ahead and discuss with your friend for another minute or two. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so let's see what do you guys think after discussion? Okay, so now more of you agree that C is not correct, right? So what is C? So C is page table lookup overhead, and we said page clustering help that. Because can some of you tell me about why you think C is incorrect? Any thoughts? So quiet, or just because you guys like, after machine learning being after human learning for quite a while, most of the time you think C would be the answer of multiple choice. All right, so let's look over each one. So first of all, is process startup cost issue could be addressed by on-demand, copy on reference and demand zero. Is this true? How come? So in Unix, right, how do we create a new process? Start with an F, end with an K, it's 4 characters, what's that word? Fork, right, not the other word. So, fork, right? So what happens when I have to be really careful to not get the wrong word. What happens when you try to fork a process? What happened? What do you need to do? What should be done during a fork? Copy everything from the original, basically a clone, right? Whatever is currently in your virtual memory address space, and also your processor states, right? They have to be copied to the other processor, right? And remember that, right? You are running in a system with 2 to the 64-bit address space. And okay, even though I only use a few megabytes of pages, it's still a huge overhead, right? So it's a lot, right? So what happens during a fork is that, say that I have a process, if I currently create 3 virtual memory pages, right? And they are in physical location page 1, 2, 3. And when I create new processes, I need to have these 3 virtual pages ready as well. And potentially, if you have sufficient amount of space on your main memory, you have to physically create copies for it, right? That's really slow, right? Remember how slow is this? You just calculated how slow is each of this? 100 nanoseconds, right? Which is now probably 200 times slower than your processor speed, right? So it's pretty slow. And the more pages you have, the more overhead you have to suffer from here. So what happens on the fork? You have to copy everything, right? Not just the processor states, but also the virtual page. So what copy on write? What's copy on write? What's copy on write?
Don't copy until the right operation.
Say again?
Don't copy until the right operation.
Don't copy until right operation, right? So what would happen is that, okay, when I create a new process, right, instead of copying everything, I just manipulate my page table in a way that I link my virtual page to my parents' virtual page. So you only copy those pages. So for example, when I try to modify my virtual page, and that's when you start to be aliasing your original link to the new page. Or on the other hand, if your parent tries to modify something, this is something that operating system dependent, right? If your parent is trying to modify something, then again, right, copy on write. So you create a new copy somewhere. Right? So copy on write is that whenever So when you fork a new process, you set all the memory pages belong to the parent process to be read only. And whenever somebody tries to write, that's when you are going to create a new physical page somewhere else. This is copy on write. So in this way, right? All I need to do is to just copy the page table instead of copy all the pages to the new process, and I'm done. Right? So it will be a lot faster. However, you are kind of like offset the cost of copy later during program execution. However, this is another story because sometimes we just want the process to start as soon as possible. So this is copy on write. How about demand zero? So demand zero is also a very interesting idea. Tell me, when you try to initialize a variable, which value you typically would do when you initialize a variable? Zero, right? So we use zero a lot in computer science. We have everything start with zero, we initialize everything with zero. If we have a page, if we allocate something, we call calc, try to initialize everything to zero. So when you create a new process, sometimes you do have a lot of space that are not filled with values of zero supposed to be. So for example, the data section, which is where you initialize the global variables. And most of the global variables, if you are familiar with the C programming language, if you just declare without assigning a value, the initialization value is also zero, right? So this is another example where you contain lots of zeros in your virtual memory space. So the demand zero is what? Whenever you have a page created, if you want the page to be initialized as zero, or the content of the page is supposed to be all zeros, instead of giving it a real page, real physical page, let's just create a page called zeros in my memory space. And everyone with zeros links there. And again, similar to copy on write, only when you try to modify something within that all zero page, we create a new copy of it. Otherwise, everyone with a zero page points to the same place. So in this way, if you have a page that contains all zeros, you don't copy, you just link that page to zeros instead. So that's demand zero. So both of them would help us to reduce the overhead when creating a process. Now, so the first one is correct. Look at the second. We want to optimize for process performance interference. So we have a local replacement policy. True? Is that true? You guys agree with that? What is local page replacement policy? What's the local page replacement policy? What's a local page replacement policy?
Process that is defining the page to like that one of its existing pages.
Okay. If and let one of my page go, but is that the only thing about local page replacement? What's the implication behind that? So the idea of local page replacement policy is that when your process enters the system, you are guaranteed to have a private or say your own few numbers of physical pages available. So those are exclusive to you. Right, so the local page replacement policy is like, okay, when I rent an apartment, I'm guaranteed to have my own room. And if you buy a lot of things, right, put them in your room. If after Thanksgiving you figure out that I'm running out of room, right, you have to figure out to kick out from your room. Right? You cannot put it in the living room, although I know a lot of people do that. You shouldn't do that, right? That's local replacement policy. So as you can imagine, no matter how many stuff my roommate bought, that won't bother me. If my roommate is well behaved, not doing stuff in the living room. That's local replacement policy. In contrast, what's a global replacement policy? Is that, okay, we don't have room. We have, everyone share this like 1,000 square feet space. You can put your stuff everywhere, right? So what you could imagine, well, let's set the privacy aside, right? If you have a ill-behaved roommate who bought a lot during the Thanksgiving, this 1,000 square feet will probably be occupied by his stuff, right? So as you can imagine, and if he is really, if the roommate is really ill-behaved, you will see that, you will feel uncomfortable, your space will be shrink. That's called interference, right? So the local replacement policy is better for avoiding program interference in that every process that is up and running is guaranteed to have a few available physical locations. So this is how local page replacement policy works, is that, okay, if I have a process and the process is always guaranteed to have 3 pages available. Whenever I want the 4th page to be used, the only thing I can do is that I have to figure out how to take out one of the physical page I use and put the new page instead of using other processing space. So in this way, as you can imagine, because everyone is guaranteed to always have these numbers of pages, it's less interference. And in fact, VMS, what's the policy that you can do? Is that when you first in, first out? Right? The simplest policy that you can think of. And there's a reason for that, which we will read in the next week. And, well, again, right, if you take a very simple algorithm, it's basically low overhead. Now, so this process has a control over the so let's see. Correct. Now, look at page process. So page process is the idea that whenever I read or write, I will try, when I read a page, I would, okay, so if you learn your architecture, you know that programs have the behavior of locality. So page processor is basically trying to explore that behavior that whenever I try to do a read write, I would try not only in those pages, the page that I'm demanding, I will try to bring more stuff in, right? And also, when I have writes, I would delay the writes and try to buffer them and try to write consecutive pages together. This is called page buffering. So the reason is actually in the table, and some of you already observed that. So if you just access the disk, and you will figure out that if you just want to get like 512 byte sector, this is what you have to pay. You have to pay the disk 6 times. However, right, if you just want to get 512 bytes from it, this is all you need to pay. However, if you are willing to read an additional 1 megabyte sequentially from the disk, this is the additional overhead you have to pay. Right? Look at that. If I just want to get 512 bytes sector, I have to pay 2 milliseconds. However, if you want to get 512 plus 1 mega, right? This 1 mega is a lot, but you only have to pay this amount more. This is like, okay, I go to buy grocery. They tell you that if you only buy this little snack bag of chips, you have to pay $10. But if you are willing to pay $1 more, I will give you a dozen. Right? This is a deal like that, right? So this is the idea, right? Is that we try to aggregate it all together, right? So another idea that also try to explore that is called page caching. Again, we like to write pages all together, right? Or read pages all together. So so how do we delay those pages that are reading, right? So then you have to manage your memory pages in different ways. So here is the additional two things that we can do is that instead of whenever you want to edit a page, you write it down. Or whenever you want to get a new page, you have to swap something out. And swap some. You create a free list, which always prepare a clean page that are ready for you to use immediately. So you don't have to swap something out when you have a page fault. Right, so when you have a page fault, if there is a page in a free list, directly use that page. And another list is called modified list. Is if I have a page that has been modified and that has been kicked out, instead of writing it down directly, I delay the write and put it in the modified list. So whenever I aggregate sufficient amount of them, I write it all together. Or if fortunate enough, I need that page again, I can put that page back. Right? So this is called page caching. And it will help, as you can imagine, right? Whenever you have a page fault, instead of serving the write immediately or try to kick out someone, I can directly feed the page. So the page fault overhead is improved. Right? So what happened with this page caching is that, well, saying that I have a process A, originally I have 4 pages. I have another process B, it has 4 pages as well. In the meantime, I maintain a free list, which I have 2 pages for free. And for example, if process A now has a page fault, in this system, because it's a system with local page replacement policy, I can only have 4 pages, right? So when I have a page fault, I have to kick somebody out. And without free list or modified list, whenever a page fault occurs, I have to swap one of the page out. But with modified list and free list is that if the page itself is clean, right, I can directly put it in the free list. If the page is modified, then I will put it into the modified list. And in the meantime, the 4th page that I want can be directed to the 5th page I want can be directed to the free list, right? So now in your system, there's only one free page, but one of the page is in a modified list. The total amount of pages used by each process is still the same. However, right, these 2 lists, they have different number of pages now. Okay. So saying that now process B also have a page fault. I need a different page again, right? I will serve the page from the free list. And depending on if the page is clean or not. If it's clean, then you return the page to free list. Otherwise, you will put it in the modified list. Okay? And if you are lucky enough, the page that you're currently pointing to, the free list, contain the content you want to swap in. then you directly redirect it here. And you have the content. So it's also a phenomenon of caching. You don't have to load everything in. So that's the benefit of reverse. Okay, so with page caching, right? So this line, it tells you with FIFO, this is the page fault rate. However, if you have LRU, which we know is probably the best in page replacement policy, you are at here. And this 10%, 20%, 30% is the percentage of page used for page caching. And as you can see, right, if you allocate more pages inside this page caching, at the end, your page fault rate could be as low as using LRU. So how is very effective in improving the performance. So as you can see, page clustering helps to reduce disk load, and page caching is also reducing disk load. All right. And some of you were curious about, okay, then how we shrink the base table overhead? It's actually the segmented memory layout in VAX VMS. And this is actually pretty similar to the modern Unix or Linux system layout. So first of all, your program, you have a code section, you have the reserve section, you have the system region. So if you have some hardware data structure, or say like basically some of the kernel space data that will be put in here, and you have your own program region, and you have your stack area, you have your code, you have your heap. So your program will be separated into these 4 different segments, and some of the segments could be shared among multiple processes. And well, no, that's not for VAX VMS. Okay, let me take it. And each of the different segments, they would have its own page table. So, but because each of the region is smaller than the whole address space, so the page table itself could be smaller. And how do you identify which segment am I? You can tell from the virtual address space, virtual address, right? So you can see what's the leading bit, the most significant bit of your address. And then you can see which page table I should reference. So you have, if you have 4 different segments, you basically have 4 different page tables, and each is smaller than the original one. And further, as we mentioned, right, in your program region, you only need to allocate part of the address that you use, either stack or heap. So that's how you reduce the page table size in VAX by creating segments. All right. So it's actually segmented memory layout. So these are the 4 mechanisms they propose in this paper. And as you might hear, a lot of them are still in use, like copy on reference, demand 0, local replacement policy. You will hear a lot in other papers. Page caching, your system now is actually crazily caching all the time. So these are the mechanisms that we are still using today. So that's the influence from VAX. So, and if you look at how Linux process lay out the memory, it's pretty similar to, somewhat similar to VAX VMS in a way that we still have the segment. And there are 2 big segments, user space memory, kernel space memory. And within the kernel space memory, we also have physical memory reserved for the kernel. And some of them could be page. So this is how Linux manage your memory system, right? And so within the kernel space, we also have a segment called kernel logical address. And this is mapped to a region that is consecutive reserved in your physical memory location that is always reserved for kernel. And one thing that you should be aware is that in Linux, this region is visible by all processes when it enters the kernel mode. So what would happen is that saying that if I have a variable called b, right? And if I declare them in a kernel space, everything in the kernel space is visible to other process if the other process is also in the kernel space. Did you hear that? So if I declare a variable b in a kernel code, when another process enters the kernel mode, it could retrieve that value. You have some idea how to implement your project now, right? Did you hear that? So if you leave something in the kernel, when the other process enter the kernel mode, you check the same place, it will read the value. Right? However, user space is completely separated. So if I declare a variable A, then this variable A will be mapped to different locations in the memory physically. So that's how you protect the value being modified by one another. However, in the kernel space, it's visible to everyone that is currently in kernel space. And that's why we have to use RCU, we have to use semaphores when you are dealing with kernel access, because they are all shared, and you have to be really careful not to have one process in a kernel mode affect others. Okay, so that's the latest layout. So now let's look at another operating system called Mach. So for Mach, this is what we have learned so far. We read a paper about Mach, but I know we don't understand Mach very well. Being honest to you, surprisingly, Mach is an operating system used intensively everywhere. However, there is not really good documents about them. So, but here is the abstraction that we learned so far. We have task threat, which is mapping to the process in Unix, and threat as the abstraction of the processor as the basic scheduling identity of processor resource. We have the port and message, which is the communication methodology between different processes in, or say different threads in Mach. And we have the abstraction of memory object, which we didn't talk a lot, but it's actually the most essential abstraction in Mach. So if you think about, and in fact, other abstractions like text, thread, port, message, they are all illustrated, abstracted as memory objects in Mach. And today we are going to talk about their memory objects. So what Mach proposed? So Mach's virtual memory abstraction is very different in terms of data structure. They are very different from other operating systems in a way that they try to be machine independent or as much as possible. So for other operating systems, what they try to do is that, oh, we try our best to shrink the size of page table, try to use this many mechanisms, try to minimize the amount of access that we need to do the translation. However, for Mach, it's focusing on how can we make the data structure more machine independent. And for the hardware part, we only treat the hardware as the cache. And in fact, their data structure doesn't necessarily need the hardware to help. So this is how they do. So again, we said, right, for Mach, they still have the abstraction called process, which they use the name of task. And each task is essentially a memory object, but within the task, they also have a lot of other memory objects. And each of the memory objects, they will have a node in something called address map. And these nodes are organized as a linked list for each of the processors. And each of the linked list nodes, they contain the information about the starting address of the virtual memory, the end address of the virtual memory, which number of this memory object is, what the protection, inheritance, previous, and next because it's for units. So we can imagine whenever I want, and then under each memory object, there will be a few memory pages associated with it. And there will be a resident page table that contains the link between the physical page and the virtual page. So what happens here is that if I'm performing a memory access, after receiving this address, the operating system will traverse the address map to see, oh, which range of the memory address is by checking the start and end address. And by subtracting the address with the starting address, you know the offset of the memory object, right? Of the memory page, and then you know which page it is, and then you can use that information as a hash input that directs you to the reverted page table. So they don't have a hierarchical page table because you think about the structure is already slow, right? Rigorous and multiple layers of interaction. So instead of using a hierarchical page table here, they just implemented a hash-based page table. And this page table will contain the mapping between the virtual address and the physical location. So everything here, they can all run in virtual address spaces, right? Because they are all operating system created. They have structures and just link lists or page tables. Nothing rely on hardware. Right? Did you hear anything about like I have to set a register or something? No. That's where they are, right? This is how they use hardware. They create something called physical map. And the physical map is actually a customized structure that when you create, or say when you modify the Mach kernel, you can tell the Mach kernel what happened and how do I need to do with the underlying hardware, like how am I going to program the TLB? How am I going to program the CR3 register? How am I going to program the page table structure in the hardware? But you can opt to do nothing. So this is the idea of that. And that's the only part that needs low-level programming. Well, I was trying to find if I can find more concrete examples, but this is the best document I can find online regarding what is PMAP. VM objects are managed by machine-independent VM system with an underlying virtual to physical mapping handled by the machine-dependent PMAP system. The PMAP system actually handles page tables, translation loops, inside buffer segments, and so on, depending on the design of the underlying hardware. Thanks, Apple. Doesn't help a lot. But that's the best I can find online. And surprisingly, if you want to figure out how the PMAP is physically done, people on the Stack Overflow tell you to read PMAP.c, read the code. And how long is the PMAP.c? It has more than 10,000 lines. So I'm not going to do it. If you are interested, you are free to do it. But the thing is that, right? Well, nobody really knows that, but everybody is using it. So now, one of the big examples is like Apple loves that. So, and compare with VAX VMS. Why do you think Apple favors that design instead of VAX VMS used intensively by Linux? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. What do you guys think? I got pretty high volume of selection on C. And because we are running out of time, so what if we just have you guys tell me about why do you think two of them are correct? So for the first one, do you think the first one is correct? Do you think the first one is correct? No? Yes, no? No, right? Why? Why not?
Because what has to be more data structure.
Right, so the data structure is pretty complex and it's all done in software without hardware acceleration. That's one part. What's the other? What type of kernel is Mach? What type of kernel is Mach? And what do we criticize about microkernel? What?
There's a lot of nodes.
There is a lot of
They have to switch to kernel.
context switch, right? So if you, okay, one thing I didn't mention a lot in this picture is that, okay, whenever you have a page fault, there's a service called pager in Mach to select which page to load from. This pager is a user space process. Did you see that? So we get all those things done in kernel space. Now we switch to user space again to deal with the pager. And when we are done, switch back. Right? Because you have a lot of context switch, right? So, and also, right? So Mach has more context switches. And some of you would argue, well, probably Mach has better page replacement policy. No, it's also use FIFO. Everybody loves FIFO, right? By default. How about the second one? Is that correct? Page table more efficient for sparse address allocation. Actually, thinking about is a linked list structure, right? So I only allocate just enough amount of page table entries and addresses for what I need. However, for hierarchical page table, you always create a lot. Right? So it's actually more efficient. And the other thing to think about that, right? For this is the and for lots of this unused area in Mach, they are just like a node in the linked list, which is more efficient. Again, right? For the process creation, right? Both of them use copy on reference, so I don't think it could be more efficient, right? However, the last one, that's the main reason, right? Mac OS is used everywhere. And surprisingly, like the first version of the Mac OS is used on PowerPC, now it's on, well, then on Intel PC, and now it's on ARM. But they never have to change the OS. Why? Because Mach's VM design is so adapted to different architectures. So that's why they love Mach. All right. So before you leave the classroom, there are a few things that I want to discuss with you. So first of all, I checked the GitHub clone, only 18. And my estimation is that you should have 25 to 30 groups, given that we allow you guys to group in 2 or 3, and with an estimation of 2.5 per group on average, we should have 25, right? Only 18 clones, and each of you is supposed to have a clone of it. I only say 18. Okay, what about the rest? Right, so start the project as early as possible and make sure that you go through all the documents before you start, and we have all this hour to help you. Reading quiz due next Tuesday for sure, and we also have midterm on next Thursday, Friday. Any 80 minutes you pick. And we don't have lectures on Thursday so that you can use your time to review. And finally, if some of you are interested about this, go ahead and read the end of the slide. You will have a simple midterm for you to practice. I know it's about a week from now, so some of you really want to start working on it. So just give you a feeling, right? What kind of problems you are going to have, right? The true midterm is something like this. And currently, I decided to have, well, I think we will have 15 multiple choice for short answer and 3 key answer questions. And here are the questions that you can potentially go through after this class. And I give you a week from now to review those questions. But you know, the questions are not just limited to the set. This is just the simple midterm. Other than that, enjoy the rest of the week. I will see you next Tuesday.
Avoiding this disaster seems impossible. My heart is beating faster, fast as it can go. 'Cause I'm overthinking every word that was never said or heard. Happy ever after? I don't think so. I'm in love.